Video 2 of Chapter 7, we are going to continue our discussion on sampling distributions. Now, previously, we had talked about two questions to explore with our marathon data, and that was, what is the average age of all the marathon runners, and what proportion or percentage of runners were from the home state of Nebraska? So we have these questions about the population. And anything we want to know about the population is called a parameter. Now, there were two things that we were interested in, a specific type of parameter. We were interested about the population mean. So again, the mean is a type of parameter. A parameter is a value from the population. We were also interested in a different type of parameter, specifically the proportion or percentage of runners that were from the home state of Nebraska. Now, for certain parameters like the mean, there are symbols that go with them, and the population mean is mu, and the population proportion is lowercase p. Now, there are other things that we could explore and want to know about the population, like maybe the standard deviation, maybe the maximum value of the population, maybe the IQR, maybe the 90th percentile. Literally, any value that you would want to know about a population is referred to as a parameter. Now again, most of the time, we are going to focus our attention on means and proportions. And in this video, we're going to discuss why in particular that we're really focused on means and proportions more than any other type of parameter value from the population that we could ask a question about. Now, since we didn't know the answers to our questions about the population, we said we should create a sampling distribution or look at a sampling distribution. And so kind of now on the flip side of the population page is a sample page, right? We said we would want to take a sample, preferably a random sample or an SRS. And so any value that we want to measure from a sample is called a statistic, which is why you were in statistics. So we use all of these values from a sample. So again, we didn't know what the true average age of all marathon runners were. So we took a sample. From that sample, we calculated a statistic. Specifically, we wanted to calculate the mean of our sample, which has a special symbol, X bar. And then for our other question about what proportion or percentage of runners are from the home state of Nebraska, we took our sample, we calculated a statistic, specifically the proportion of runners from our sample that were from Nebraska. And that had a special symbol, P hat. Now again, from our sample, we could calculate a variety of different statistics, like the mean and proportion, or the standard deviation, or the IQR, or the max or the min, or Q1 or Q3, or the 90th percentile, or any other percentile value. So again, we are going to focus our attention really just on means and proportions. So again, if we want to know something about our population, we are going to calculate we want to know about a parameter value. A parameter is a specific value from our population. We are focusing on means and proportions as specific parameters that we want to know about from our population. So if we want to figure out those values, we will need to take a sample and calculate a statistic. So if you kind of notice, there's a little play on letters here. From a population, we calculate a parameter. From a sample, there we go. From a sample, we will calculate a statistic. So notice S goes with S, P goes with P. Parameter is just the generic term that means any value taken from the population. These are all examples of parameters. A statistic is a value taken from a sample, and these are all of the different types of statistics. Not all of them, but just a sample. Well, that's kind of a poor choice of words there. These are examples of statistics that we could take from a sample. How about that? So our questions, we are really just going to focus on, well, we'll talk about both. We'll do both. Question 1 and question 2. So who is the population? Our population is all 974 runners. Now, who is the sample? Well, previously we took 3 different types of samples. We took samples of size 10 runners, 20 runners, 30 runners. I would say let's focus on the big one for now. So who is the sample? We'll say our sample of 30 runners that we took previously. So the population is all 974 runners, but we're only collecting information from 30 of our runners. What is the parameter of interest? What do we want to know about the population? And so this kind of got split up between our 2 questions that we explored previously. So one parameter was the mean age of all runners. Specifically, that was mu. We're wanting to know, what is mu? What is the mean age of all these runners? But we also had a second question that we wanted to explore, and that was the proportion of runners from Nebraska. And that was our population proportion, lowercase p. Now you might ask, can we use capital P? It has to be lowercase p. Capital P represented probability back in first semester. All right, now what is the statistic? So we wanted to know these 2 values. We want to know the mean age and the proportion of all runners from Nebraska, but we don't have access to that entire data set. Now I did, but you don't, right? So your next step was to take a sample, and from that sample, you took 30 runners and you calculated what their mean age was and what proportion of those 30 runners were from Nebraska. So one of our statistics was the mean, the mean age of the 30 runners. So again, we calculated a sample mean, an X bar, and then for our other question, we calculated the proportion of 30 runners from Nebraska. And so again, we calculated just from 30 runners what percentage were from Nebraska. So again, we're using X bar to try to estimate roughly what the population mean is. We're using the sample proportion, p hat, to help us estimate, hopefully closely, what the true proportion is for all of the runners from Nebraska. Now, can any sample statistic be used to estimate its population parameter, right? That's what we were just talking about. Can we use X bar to estimate mu? Can we use p hat to estimate p? Well, let's go back a little bit further. Can we use any of these sample values to estimate their corresponding population values? And unfortunately, that's not true. So some statistics produce too much bias or error to closely estimate the parameter of interest. And this type of statistic would be called a biased estimator. But if the statistic estimates a parameter with little bias or error, then that statistic is called an unbiased estimator. Now, previously I said the main reason that we're really going to be talking about means and proportions is because means and proportions are examples of unbiased estimators. They have very little to no error in their estimations of the true population parameter values that they're trying to estimate. But I'm going to show you an example of a true unbiased estimator, and I'm going to show you an example of a biased estimator. So how do we know if something is biased or unbiased? Well, the criteria is this. A statistic is unbiased if the center of its sampling distribution is approximately the same as the population parameter. A statistic is unbiased if the center of its sampling distribution is approximately the same as the population parameter. So again, I'm going to show you two examples. I'm going to show you first an unbiased estimator, which should look familiar because we have recently discussed it. And then I'll show you an example of a biased estimator. So was our sampling distribution using the sample mean of ages a good unbiased or bad biased estimator for the population mean age? So I have a little snapshot of a sampling distribution that a couple of my classes made previously. And this was the kind of beginnings of the sampling distribution that we started to create together. And again, this isn't the true sampling distribution because there would be, remember how many dots there would have to be, like how many different samples we could take? Like this is nowhere near the true sampling distribution. But this is giving us a good picture, a good idea of what that sampling distribution is going to start to look like. So each of these dots represents one of my students' average age or mean age of their random sample of 30 runners. And so what we found out based on our sampling distribution that we were starting to create, a lot of my students thought that the mean, the center of this sampling distribution that we were starting to create looked like it was about 39 years old. Okay, so that's what I have mu sub x bar. The center, the mean of what? Of the sample means, which is kind of a mouthful to say. The mean of the sample means was about 39 years old. Now, I shared what the true average population parameter age was, and it was 38.81. So is the mean an unbiased estimator? Is the sample mean an unbiased estimator of the population mean? So again, the definition we were using, the criteria that we're using, is a statistic is unbiased if the center of its sampling distribution, and here is the center of that sampling distribution. We thought it was about 39-ish. Is it approximately, this is a key word here, is it approximately the same as the population parameter? Well, the true population parameter mean age was 38.81. Now, the key term there, that approximately, is great because, look, we thought it was around 39, and the true mean age is 38.81. Are they approximately the same? Are they really, really close to each other? And I would say yes, these are approximately the same as each other. So the sample mean is an unbiased estimator of the population mean because the center of the sampling distribution is about the same as the true population value. Now you might be wondering, but how would I know what the true population parameter value is if I don't have access to the entire data set? And that's a good point to bring up. So this is kind of considering more theoretically if I know the true population value. But if I don't know the true population value, then you could look into what statisticians have determined which statistics are biased and unbiased estimators based on really a lot of research and math and a lot of deep diving math and statistics, to be honest with you. Now, the other example we're going to take a look at is the median. Is the sample median a biased or unbiased estimator of the population median? So what I did was I took my population and I figured out what the mean, not the mean, sorry, backtrack, what the median age is for all 974 runners. And I found out that the median age was about 39 years old, actually. Now, what I did was I took small samples of 3 runners, and I figured out what is the median age of those 3 runners. So if you think, if I've got 3 runners, 1, 2, and 3, and I were to put them in chronological age order, then the middle person is always going to be the median, right? So what I did was I took the median age. It's always that middle person as long as we're going from youngest to oldest or oldest to youngest. And then I graphed them on here. So I did that many times. Again, this is not the true sampling distribution, but it's just that small snapshot of doing it so many times. So then what I wanted to look at was, what is the center of this sampling distribution? And that's what this mu sub m represents. Each of these dots represents the median age of 3 runners. And you can see I had I had 3 people that were, young, or up here I had 3 people that were pretty old. But the center of the sampling distribution is right around in here. So, is the median an unbiased estimator? Well, the center of the sampling distribution is 36.63 years old. And the true population median age is 39 years old. Are these approximately the same as each other? Now, some people would go, these are close enough. We're, less than 3 years apart from each other. But they really have to be very close to each other. So I would not say that these are approximately the same. So the median is not an unbiased estimator. So the sample median is not a good estimator of the population median. Now, there are some exceptions to this, and I did some research. And if the population follows a normal distribution, or something very close to a normal distribution, then the sample median can be an unbiased estimator of the population median. But if you remember previously what the population shape was for ages that we explored earlier, it was not approximately normal. It was slightly skewed. So because our population shape was not normal, then that made our sample median not a good estimator for the population median. Now, there are 4 situations regarding bias, error, and variability. Variability is just in terms of how much spread we have. So we can have high bias, high error, and low variability. So low variability, notice if we think of our target here, low variability means we're very consistent, but we're off center. We have high bias. We want to be right on the bullseye mark here. So we're always shooting for that bullseye. And so in this example, we're consistent, but we're off-center. So we have high bias, we have high error, we're off-center, but we have low variability. All of our points are really close to each other. We're very consistent. Number 2, we can have low bias with high variability. So high variability, our points are really scattered about, but there's little error. They're pretty centered right around the bullseye here, but we're not exactly hitting the bullseye, but we are centered around that bullseye. Number 3, high bias and high variability. So high variability, our points are really scattered about, and we're not exactly near the target. So notice all of these points, they're centered more around here, which again is off-center. And then the 4th one, this is the one we really want to shoot for. We want to have low bias with low variability. So we want to be on point, we want to be on center here, and we don't want to be too far away from our bullseye. Now you might be wondering, what does this have to deal with our biased versus unbiased estimator? So let's take a look at an example. So here's 4 sampling distributions. And in each of these 4 situations, we are going to call this arrow where the population parameter value is located. Now, you might be wondering, what type of parameter? Is this the mean? Is it a proportion? Is it a median? Is it standard deviation? What type of parameter? And honestly, it doesn't matter what specific type of parameter it is. But we're saying the true value of the population is right where the arrow is at in all 4 of these situations. So what we're going to do is we're going to take either high bias or low bias and match it up with high variability or low variability to describe each of these 4 situations. Now, let's start with A. A, if you look at our sampling distribution, it doesn't look very centered on our arrow here. It looks like the mean, the center of our sampling distribution, is to the left of the true population parameter value. So I would say we have high bias in this situation. We're off center. Now, in terms of variability, do we have small amount of spread or do we have a bigger amount of spread? And when I look at this sampling distribution, it's stretched out pretty wide there. So I would say this is high bias with high variability. And this is definitely a situation that we don't want to have in a sampling distribution. Now B, on the other hand, if you notice here, everything, our sampling distribution is fairly centered, right, on this arrow. So I would say this one has low bias. And in terms of variability or spread, there's not much spread here. This is low variability. So this kind of matches up with what we saw with an unbiased estimator. And so we want that center of our sampling distribution to be approximately the same as our population parameter value. So this is the ideal situation. Now for C, now here I can automatically see we've got high variability. We have a very spread sampling distribution. Now, in terms of bias, though, I would say the center of this sampling distribution is roughly around the population parameter. So we are centered on our population parameter, but we got too much variability, too much spread. And then for D here, in this one, you can see that we've got low variability, right? We have very little spread, but we are off center. We have high bias. We're supposed to be centered right here, but instead we're centered way over here. So this was like that example of the target where they were all off center, but they were really, really consistent with each other. All right, so the population parameter is 75. So I'm telling you the truth about the population. It is 75. So I'm going to highlight 75 for all four of these statistics and these sampling distributions. Which statistic or statistics are unbiased estimators? Now remember, the criteria that we were using to determine if a statistic was an unbiased estimator of the population parameter was if the center of its sampling distribution was approximately the same as the population parameter. So when we look at statistic A, is this sampling distribution up here, is its center about the same, approximately the same as 75? And I would say if I'm looking at this sampling distribution, yeah, I would really think the center is around 75. So I think statistic A would be an example of an unbiased estimator. I think its center of its sampling distribution is about the same as the population parameter. Now, what about for statistic B? Does the center of this sampling distribution, is it about the same as the population parameter value of 75? And here I would say it is not, right? It looks like here's about the center, which is somewhere between 75 and 100. I don't know what it is exactly, but it doesn't really look like that it's going to be an unbiased estimator. We are overestimating what the true value is for the population. We're above the mark here. Now for statistic C, does this sampling distribution look like it's centered on 75? And I would say it does, right? Now we've got a little bit more variability involved here. I would say the standard deviation is higher in this sampling distribution than it is in statistic A. But you know what? I would say this would be an unbiased estimator. The center is about the same as 75. And then what about for statistic D? Does the center of this sampling distribution look like it's right on or about 75? And I would say it is. The center of this looks like it's roughly uniform in shape, right? It's kind of going up and down throughout the entire thing. It's not perfectly uniform, but it's roughly uniform. And so I would say statistic D would be an example of an unbiased estimator. So A, C, and D are unbiased estimators. B was a bad unbiased estimator. It was a biased estimator in the end. Now, what I want you to explore is which of those three unbiased estimators, A versus C versus D, do you believe would be the best unbiased estimator? Do you think A is the best unbiased estimator? Do you think C is the best unbiased estimator? Or do you believe the statistic D is the best unbiased estimator? And so consider that, and then think about what would make a statistic a better unbiased estimator than the others. And that'll be something that we will explore in class tomorrow.